we'd like to figure out under what circumstances, so there's this unknown quantity in here, h, in our third vector. And we'd like to know, under what circumstances does that third vector belong to the span of the first two? So to write that as specifically as possible, for what h does V3 belong to the span of V1 and V2? And the contention is that this has something to do with a system of linear equations, right? We should be able to set up a matrix and row reduce it, and that should somehow answer this question. But why? I find there's enough confusion to go around in linear algebra in talking about span as a concept that we should, this is a good problem for us to come to grips with that. So let me ask you, what does the span of V1 and V2 mean?
It is those vectors multiplied by another number and added together.
Right. In other words, the shorthand for that is linear combinations of V1 and V2. So this is the set of all linear combinations of the vectors V1 and V2. So it's the set of all vectors that we can express as some constant, let's call it x, times V1, plus some other constant, let's call it y, times V2. And it's the set of all such linear combinations for all possible numbers x and y, all possible real numbers x and y. So that's the definition of what the span of two vectors is. And now we just have to ask ourselves, what is the cost of ownership, membership in that span? What does it mean for one vector to belong to the span? If the span is a set of all linear combinations of V1 and V2, then what does it mean for a third vector V3 to belong to that span? How would we know if V3 belonged to this span? Was an element of this set? I'm going to write it again in English down here on the bottom. The span is the set consisting of all linear combinations of V1 and V2. It's over here. So that's what the span is. And we're trying to figure out what it means for V3 to belong to this set.
There has to be some number, x and y, that multiplies by V1 and V2, that will give you V3.
Exactly. If V3 belongs to the set consisting of all linear combinations of V1 and V2, that must mean that V3 is one of these. That V3 is a linear combination of V1 and V2. In other words, that there exists an x and a y such that V3 is equal to x times V1 plus y times V2. So let's get that down here. So if V3 belongs to this span, that must mean that V3 is equal to x times V1 plus y times V2 for some real numbers x and y. In other words, this vector equation, x times V1 plus y times V2 is equal to V3, has a solution, x comma y. What buzzword is that? What does this vector equation have to be? If it has a solution, what does that make it? Consistent, right. So one-to-one would address the uniqueness of this solution. We don't necessarily need the solution to be unique, but we do need the solution to exist. So we need there to be a solution to this vector equation. For some values of x and y, we should have x times v1 plus y times v2 is equal to v3. So now that this is written as a vector equation, we've taken this concept of span And because span is the set of all linear combinations, and because every vector equation expresses one vector as a linear combination of other vectors, now we have a vector equation that we can investigate the nature of its solutions. So we're looking for values of h, this unknown number in our V3, that make this a consistent system of linear equations. So now we have a vector equation. We can set up an augmented matrix and start our row reducing. So what is our augmented matrix going to look like that corresponds to this vector equation?
1, -3, and 5.
1, -3, and I think it's 2 there, isn't it? Oh, no, you're reading across the top.
Oh,
Thank you. No, you're right. So 1, -3, and then on the right-hand side, 5.
No, -3, 9, -7.
-7.
And then 2, -6, and then 8.
2, -6. And there's our unknown h. There's our wild card.
So would you set it equal to 0?
Well, that's just it. So what I'm going to do instead is I'm going to put a little augment bar here in this matrix. Because the 5, -7, and h, that's V3, and V3 is already our right-hand side of this vector equation. So let me declutter this piece on the right here to really drive the point home of what this matrix equation is representing for us. It's representing the vector equation x times v1, and v1 was 1, -3, 2, plus y times v2. v2 is -3, 9, -6, is equal to, so where my equal sign is in this equation is right there, and my right-hand side is v3, 5, -7h. So we don't have any zeros on the right-hand side or anything. What we have on the right-hand side is V3. So in our augmented matrix, 5, -7h is our right-hand side. So this augmented matrix is going to tell us whether or not 5, -7h is a linear combination of the first two columns, 1, -3, 2, and -3, 9, 6. -6. Because again, we want to know what h satisfies, or what h is going to make this a consistent system of equations. So if we imagine that we've row reduced this set of equations, first of all, how many pivots can I have? I can have at most 2 pivots. How come? Yeah, I have 3 rows, but only 2 columns. And since we can have at most 1 pivot per column, I can have at most 2 pivots in this system. So let's pretend that I have a pivot in the first row and a pivot in the second row, just for fun. But then that's going to leave the third row without a pivot, which means in the reduced row echelon form, what is that third row going to be? Actually, it doesn't end up being a free variable because the rows correspond to equations instead of variables. But definitely what the third row will be, if we reduce it completely, if the row doesn't have a pivot in it, then that row is going to be a row of all zeros. Because we can use the pivots to eliminate any other entry that we had downstairs that was not a 0. So that last row of our reduced matrix is going to be zeros on the left-hand side. So if our goal is consistent system of equations, what else do we have to see here that's going to indicate consistency versus inconsistency? I should make these pivots little squares instead of circles, because the circles look too much like zeros.
Would that mean that h equals 0?
Well, not necessarily, but close, right? Because whatever we have right here on this side of the equation, if this is a consistent system, that had better be 0. In the lower right-hand corner, whatever we get when we finished our row reduction in this lower right-hand corner, we better have a 0 if this is a consistent system. Otherwise, if I have anything else, if I have something non-zero down there, then our system is inconsistent. That was our sort of a day one. We didn't call it consistent, inconsistent back then, but on day one we realized that having 0 equals something non-zero come up in a solution of a linear system means that the system was inconsistent. It means it had no solution. Right? So if we want consistency, we want a 0 right there. And so where the work comes in is we have to figure out what happens to our h that we start with in the process of that row reduction. Because we can't necessarily expect that after all of our row operations are done, that the entry that's down here is actually still just equal to h. It's going to equal to some combination of h, and maybe the other numbers in this system of equations. But if this is what we're shooting for, let's do the row operations to figure out what it's going to take to get it. So as soon as we've cleared out the first column to get that pivot by itself, here is our reduced, well, at least our row echelon matrix. Now what? What is this reduced form telling us? If h is equal to 10, then this very last equation will be 0 equals 0. And that will make us happy. So if h equals 10, then we can go back in here and say, oh, okay, well then that makes this entry 0. But I'm still skeptical. Jocelyn, why is there no solution? That second row is a problem. Even if I make that last equation read 0 equals 0, we still have a second equation, which no matter what value h had, is still going to read 0 equals 8. And so we are up a creek on this problem. In other words, no matter what value h has, this vector v3 cannot be written as a linear combination of v1 and v2. So there is no solution. For no h does v3 belong to the span of v1 and v2. In just a second, I want to make this visual so we get the picture of what that span is doing for us. But are there any questions about the algebra that we did here? So here are these three vectors. And I've set them up here as kind of the columns of a matrix. So our v1 is right there. v1, here's v2. And then there's an example of a v3, where here for this v3 we've chosen h equals 1. But taking a look at the vectors v1, v2, v3, what relationship do you notice exists between v1 and v2? Can you tell from this diagram? Let's go away. There we go. Can you tell from this diagram what relationship exists between v1 and v2? Maybe if we spin around a little bit here. Remember, these are vectors living in 3 dimensions. v1 and v2 are in fact parallel to one another. So if I try to look at the span of v1, v2, and v3, the best I'm going to do is I'm going to get something that looks 2-dimensional like this does, right? This parallelogram sitting in 3 dimensions. Because v1 and v2 are parallel to one another, that means that linear combinations of v1 and v2 can only give me what? If I take some linear combination of v1 and v2, I'm guaranteed to get something which also is parallel to v1 and v2. So the only v3s that I can get as a linear combination of v1 and v2 are v3s that live along this line, because v1 and v2 were parallel. Which means that no matter how hard I try, by adjusting this last component of v3, so changing the h is just kind of changing this around. But don't be fooled by the perspective. Even when I put this at about 7, still all I'm doing is I'm kind of spinning that third vector around the line formed by v1 and v2. And there's no way for me to make that third vector lie in the line that v1 and v2 lie in. And so I can't ever express v3 as a linear combination of v1 and v2, because there's no way to adjust this last coordinate to make v3 on the same line as v1 and v2, because v1 and v2 are parallel to one another.